Okay, we're going to go over sampling methods and the central limit theorem. Okay, so why would we sample a population? Would it really, or why would we examine a sample instead of a population? It really comes down to resources and getting the maximum amount out of our, out of what we're measuring for the resources that are allocated to measure that sample versus the population. Okay, so if we can use less resources to get more or less the same result, wouldn't you want to use less resources to get more or less the same result? And so that's what it comes down to. If it's too expensive to study an entire population, then we're going to look at just a sample. And if that sample is still, we know that that sample is accurate to within a certain degree, then that's what we're going to do. Is it really worth an extra $20 million to gain an extra 1% accuracy in your data? And for some situations it might, but very rarely is that ever the case. So also it's very time consuming to contact all the members of a population. Once again, time is a resource, money is a resource, and also you don't want to destroy all of your samples. If you are an individual testing wine, you're not going to want to drink every single bottle of wine to be able to test, to determine whether or not it's quality wine. You only want to sample as little as possible to get the best or most accurate assessment of what it is that you are assessing. Okay, so the probability sampling methods, we're going to go over 4 sampling methods. The first sampling method is the simple random sample. This is what is most widely used. And with this, you basically randomly sample from a population. It's just random numbers, right? And so, for instance, if you were to have 750 Major League Baseball players, you would put all of their names right in a row, in no particular order, and you would number them, or, they really could be in a particular order. It really doesn't matter. But you number them from 1 to 750. Okay? And then in a simple random sample, you randomly pull 10 numbers, and those 10 numbers are going to be your representatives in the sample. Before computers, which there's a really easy way to do this in Excel. So I'm going to pull up Excel. Let's see here. Equals rand between. Okay, and let's do 1 and 750. So there's your first one. Let's bring it down to 9 and bring it up to 10. These are 10 random numbers between 1 and 750. So if you were to put all 750 individuals, which here I'll zoom in a little bit so you can see the formula, rand between 1 and 750, and then I just dragged it down, and these are all just random. And then if I double click, every time I double click, it gives me a whole new random set of numbers. And 667 is a random number, 393 is a random number, 199, every single one of these. Now you notice here that gave me 404 2 times, which that's, it's a random number. In this particular situation, you might need to pull new random numbers, or, say if it's, just pull a new random number just for that 404. Going back, let's see here. Before we had random number generators, there was an individual who actually published a book of random numbers, and you would randomly choose, you would randomly choose numbers from the book, and when you randomly chose numbers, it would tell you which individual to pick. But we're not going to have you do that. So in a systematic random sample, um, we have your entire list, or you don't have a list, either one. But essentially, it's like when you're at a grocery store, right? You would look at possibly every seventh individual that comes into the grocery store, and you want to determine how long that individual stays in the grocery store. So the seventh person stays in there for 30 minutes. The 14th person stays in there for 12 minutes. The 21st person stays in there for 39 minutes. And you just keep on taking every seventh person, for the first 2 hours. Now, if I take every seventh person for the first 2 hours, is that really going to give me an accurate representation of the entire population? And the answer is no. It's only going to give me an accurate representation of the population that comes in from, 6 a.m. to 8 a.m. And so it's very important that when we look at our samples, that we understand what this is a sample of. It is a sample of a population of individuals that come in from 6 to 8 a.m. So, the individuals that come in from 6 to 8 a.m., could that be an entire population? That is representing the population of people that come in from 6 to 8 a.m. Now, is that representing the entire population of everyone that ever, goes into that store? Definitely not. Just be very aware that, there's different ways to look at populations. So a stratified random sample is when you essentially create groups that these individuals can fall into. Previously in this course we created classes. So if you create classes, for instance, if you have a continuum of individuals from 0 up to 100%, or down here we've got firms that have profitability. These could be marketing firms. There's 5 marketing firms that have a deficit. There's 115 marketing firms that have 0 to 10% profitability. 10 to 20% of firms that, or 189 10 to 20% profitability, and so on and so forth. And so when you're sampling, you take a percentage of the total number of individuals that are, or the total number of individuals that are in that strata. So right here we have 5 strata. In the first strata there are 8 firms, and notice they pulled 1 person from the first strata. They also only pulled 1 person from the 5th strata. Now there's an issue with only pulling 1 person, or 1 firm, 1 representation from that strata. And the reason why is because do you really want 1 person representing all 8 of those people? Now it could be that 1 person will suffice. But it could also be that 1 person is, an outlier, and, can't really be used to generalize to all 8. So I would highly suggest that you don't ever take just 1 sample, that you always have 2. Another example of this is, well, we'll get into that in just a minute, but, yeah, so that's stratified random sampling, breaking them up into essentially classes and then pulling representations from each one of those classes. So a cluster sample breaks up by area or by some sort of other boundary. For instance, right here we've got different counties, and we want to know, information about individuals in each one of those counties. In Cook County, that's where Chicago is. And is Chicago going to be a lot different than, say, Kendall County or Grundy County? Yeah, they're completely different counties. And so the government policies shouldn't be the same in every single one of those clusters. If I were to just look at the state of Illinois, Well, part of that is the state of Illinois up to Lake. Kenosha County starts Wisconsin, and I believe Lake County or Porter, one of the two, starts with Indiana. Yes, Indiana. Um, and so, do we really want to generalize for the entire state of Illinois that they should, that everyone should be utilizing the same government policies? And the answer is no. We want to know for each individual cluster what's the most important for that county to run. Another instance would be, if you have employees at a store, you have natural occurring boundaries of positions, right? You have cashiers, you have individuals that stock. Then you also have individuals, you have managers, and you could take a sample from the managers, a sample from the cashiers, a sample from each individual area of working inside of that store. That would also be a cluster sample. All right, so here is another really important term that y'all need to know inside and out, and that is sampling error. Sampling error is the difference between a sample statistic and its corresponding population parameter. For example, if you sample 10 cashiers and there's a total of 60 cashiers, the 60 cashiers would have a very specific mean on a score. And then you have, the 10 cashiers from the sample, and the difference between the sample mean and the population mean would be what's referred to as the sampling error. And sometimes we know the population mean, sometimes we don't. And we'll get into that a little bit later of how we can establish norms and be able to determine confidence intervals and all sorts of other things and determine sampling error without actually having the population mean. Okay. When we have a sample, it's pretty unlikely that it's going to be exactly equal. In this particular situation, we have the Foxtrot in numbers of rooms rented in June. The mean number of rooms is 3.13. If you take a random sample, take 3 random samples, we could look at 4 on June 4th, June 9th, and then we could also look on June 14th, and you notice the mean of that. So 4 plus 4 plus 3 is 11. 11 divided by 3. What is that? Let's pull that up. Let's see here. We've got 11, 3.66. So 3.66 is pretty close to the 3.13, but it's not. So the sampling error, let me pull that up again, would be 3.66 minus 3. Which the sampling error would be 0.53667. So that's how you can calculate the sampling error. You look at the sampling statistic and the corresponding population parameter, and you determine the difference between the two. Alrighty, that wraps it up for this lecture, and we'll move on to the next one.